On the 5th of June 2012, the last Venus transit of our lifetimes occurred. This is the story of one man who travelled halfway around the world to see it. Now, historically, the transit of Venus is how we discovered the size of the solar system, and it's subsequently allowed us to discover how far it was to the closer stars. If you simply watch the path of Venus in the morning or the evening sky, you'll see that it climbs higher and higher, getting further away from the sun, then goes back towards the sun. The point at which it's in its highest in the sky is called its greatest elongation, and it's a relatively simple geometrical step from there to calculate the ratio of the size of the Earth's orbit to Venus's orbit. However, that doesn't tell you how far away from the sun you are, or how far Venus is from the sun. It just gives you the ratio of the two. Now, Halley, that's the guy with the big comet named after him, realised that if you have someone standing on the North Pole and someone on the South Pole, for the simple reason that it's actually quite easy to work out how big the Earth is, that it would be possible from the different apparent paths that Venus took across the sun that you could work out how far we were from the sun. Look, here's a little mock-up with the relative distances. In the first instance, I'm on the North Pole, and in the second instance, on the South Pole. And from the different apparent paths, you can work out how big the sun is and how far away from it you are. So if I double the distances of everything here and zoom the camera in a bit to keep the apparent size of the sun the same, you can see that the path difference between the North Pole and the South Pole is different. And that's how you can calculate the distance of the Earth to the sun. Now, it turns out that the solar system is actually a pretty big place, so it turns out measuring those tiny path differences is actually quite tricky. However, the whole transit takes place over about 6 hours, which means that you can make timings far more accurately than you can measure the differences in those angular paths. So, in order to measure the distance to the sun, you need 2 accurate timings of the transits from 2 different locations on Earth. Unfortunately, I could only make one, and my reckoning was the best place where you'd have the best chance of seeing it was on the biggest mountain on Earth. And no, that's not the tallest mountain, that's the biggest mountain from the base to the summit. And that's the volcano, Mauna Kea, which constitutes the big island of Hawaii, up near the observatory. Plus, this offered an unexpected opportunity to swim with the turtles in the Pacific, which I've got to say, turned out to be an amazing experience. And on top of that, you can see this lava lake from the big island of Hawaii, where you can actually see the fiery heat that permeates much of the Earth. Now, transit day itself was far from ideal, with high winds, plus the summit was off limits to everyone who didn't take this shuttle bus, and I had too much equipment for that. So I set up about 2/3 the way up the mountain. Well, that's 2/3 the way that's above the water anyway. That's some 10,000 feet, almost 2 miles in the air, but still a full mile short of the summit. Okay, so that's me. I've made it to Mauna Kea. And so the Keck Observatory is up there somewhere, and it's a good thing that I've not gone up there because it's windy enough down here. So the transit's getting towards the end, so the sun's up there, and hopefully I'll get 3rd and 4th contact down here somewhere. So what have I got? I've got the 180-degree time lapse going here. This is all the stuff that I brought with me. And this is the optical setup. So I've got the H-alpha telescope here, and so that just looks in one frequency of light. And then I've got the the Maxitov Cassegrain here. The Maxitov is just running at prime focus, whereas both of these are taking video. As you can see, wonderfully custom-made gear. So, let's set the guy up. The video was then processed using Registax to yield individual frames that were then put together in Sony Vegas. The third camera with a 180-degree fisheye lens kept an eye on the whole proceedings. So there, that's me, that little orange blur there, and the transit starts at about midday and ends near sunset. Incidentally, one of the most gratifying things about watching this transit was just one of those great moments where you actually get to feel the solar system in motion. I mean, not only do you get to see Venus track across the surface of the sun, even with my poor equipment, you get to see the evolution of the solar flares over that period of time. I mean, many times I've watched Venus crawl out from behind the sun and approach the Earth on the inside track, but you only get to see its movement from day to day. Here you could watch this silent ballet as this mighty planet with its almost unimaginable momentum quietly sails in front of the sun. It was almost a profound moment that brings the solar system to life. I mean, really, how many times can you actually watch the solar system move? You see, all the time that Venus was on the upper side, that means that you see it after the Earth's rotation obscures the sun. That is, you see it in the evening sky, after sunset. And then, when it's moved in front of the sun, you see it before the Earth's rotation reveals the sun. That is, you see it at sunrise. And yeah, I travelled halfway around the world to see that. Because you see, the next one of these is in 2117. And even with our advancing medical technology, I don't think I've got a snowball's chance in hell of seeing that. But it does make me wonder what the next civilization that looks up in the sky and sees that little black disk track across the surface of the sun will look like.